This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. In the last lecture, we started the discussion of the turbojet cycles, how to modify the basic turbojet cycle and make it to be more practical in terms of those currently used today. So instead of using pure turbojet cycle, one major modification is a turbofan, which is you put a fan in to drive a large amount of air going through the engine, but only a fraction of it going through the combustor. So there is a bypass ratio which we defined. So that's a fraction of the amount of air not going through the combustor versus the amount of air actually going through the combustor. Right? And the other one is called turboprop. So turboprop is using a similar idea as a turbofan, but it's get rid of the engine cover or the we call nacelle. So this allowing even larger bypass ratio can be realized. So we discussed that there are two rules of thumb in terms of producing higher thrust and producing more efficient cycle. One is you want to move a large amount of slow-moving air instead of a small amount of fast-moving air. And the other one is you want to match the jet velocity with the aircraft design velocity. So if these two velocities are very different, then the kinetic energy that you produced from this thermodynamic cycle will not be used efficiently. Right? So in terms of the TS diagram, if we have the one which is the basic turbojet cycle, if the state 5 is a turbojet, I have the 5 prime and the 5 double prime, which case is for the, if I call one is turbofan, the other is turboprop, which case more like the turbofan and which is more like turboprop. So let's write the first one, which is 5 to 6, that's corresponding to the pure turbojet, where we say that T4 minus T5 equals to T3 minus T2. The turbine work equals to the compressor work. So that's the theoretical one for the turbojet. So 5 prime is 5 prime corresponding to more of the turbofan or turboprop. The temperature difference from 4 to 5 corresponding to what work? What energy term? Turbine work, right? So if I have the 5 prime, which means there is more turbine work versus compared to say 5, but the double prime has even more turbine work compared to the single prime case, right? So in terms of turbofan and turboprop, which case has more turbine work output. Yeah, turboprop. So turboprop should corresponding to 5 double prime, and the single prime corresponding to the turbofan, which is, if you consider the turbojet is an extreme and the turbofan doing somewhat more turbine work, but still producing, still using a large fraction of the energy for the thrust. So that's corresponding to 5 to 6 step. And the turboprop has a even more turbine work and a less amount of kinetic energy as the output. Right? So if you have the 5 prime to 5 to 6, that corresponding to low bypass ratio. You can consider that's like a turbofan. And the 5 double prime to 6, that corresponding to high bypass ratio. So if I get rid of the state 5, and from the 4 directly to 6, which means without state 5, then we have the case that we know before. So basically, in this case, you do not have a nozzle. All the work, or all the useful output will be the turbine work. So that corresponding to the cycle that we discussed just before this, which is everything is all the useful output is a work or shaft work. That will be corresponding to the Brayton cycle. So by state 5, I mean get rid of the nozzle, right? Certainly not get rid of the turbine. Turbine must be there in any case. And in terms of the propulsion, this can also possible. So Brayton cycle, as we said, that's for the power generation in most cases. But for the propulsion, you can also output all the shaft work for the propulsion purpose. So one application is the helicopter. Helicopter running on gas turbine, and the output is used to drive the blades, and that's in the form of the pure shaft work. And the other one is actually called turbine shaft, turbo shaft. So that's another type, turbofan, turboprop, then the turbo shaft. And other than the aviation, if you're using the gas turbine for ships, the useful output is also shaft work, pure shaft work. So it's also used for ships, and also when you're using the gas turbine to drive a military tank, that's also pure shaft work as the output. So in other words, if you're using a gas turbine for propulsion, that's not necessarily you always output the kinetic energy. You can also just output the shaft work using the shaft to drive the propeller or the other drive train system. All right, so that's the variation of the turbojet. The other feature related to the turbojet is something called afterburn. So afterburn is something that in the situation that you need additional thrust, you want to add some additional heat or additional enthalpy after the turbine, but before the nozzle, so that you have additional enthalpy that can be converted to kinetic energy at the nozzle. So that's called afterburn. So additional heat added before nozzle for higher thrust. So you can consider there is a situation this kind of additional thrust would be needed. One of them is shown here. So if you have a jet fighter which is on board an aircraft carrier, and the distance for the aircraft to take off is always limited, and you want the aircraft certainly to take off successfully within the short distance. So in that cases, you want to turn on the afterburner to give you additional thrust, so the aircraft can take off within the limited length that is available there. So that's the one of the case which you can see the afterburner being turned on, and you can see from this red in the from the back of the aircraft. Right. So that's application of this would be short distance takeoff, or during a dogfight. The jet fighter is often need additional thrust in order to try to catch up the opponent of opponent fighter, or it want to leave the dogfight quickly. So that's also a case they could turn on the dogfight and turn on the afterburner. So in terms of the system, we can see that we have a compressor, then combustor, then the turbine, then the afterburner, then going in the nozzle. So in terms of the energy, you just add additional energy so that there is more available to be converted to the kinetic energy and to produce thrust. Right? And in terms of the TS diagram, so if we have 1, 2, 3, and 4, so if 1, 2, 3, 4, 5, 6, 7. So at the state 4, which is leaving the combustor, we're going through the turbine to output some work, and then getting to the afterburner. Afterburner is a similar process as the combustor, where additional enthalpy being added. So it's a constant pressure process, going up to the state 6, and then going down to produce the kinetic energy. So that's where the afterburn process is there. So you can tell this part is related to the turbine work, and this part is related to the nozzle producing thrust from the 6 to 7. All right. So if you don't have afterburner, you will go from the 5 directly to this constant pressure line. But with afterburner, you can have a larger enthalpy available, be converted to the kinetic energy. And this process actually, if you're looking at the TS diagram, that's similar to something we discussed before with the Brayton cycle. It's related to in Brayton cycle, when we discussed that if we want to maximize the turbine work output, there is a process called reheating. Right? The purpose of reheating is to, there we said we want to keep the gas volume, specific volume, as large as possible so that it can output more work at the turbine. So there, what we did is the reheating, basically you add additional heat to the system to keep the gas at higher temperature, so that it can produce more work. Here is in terms of TS diagram, that's quite similar. You just add additional enthalpy, but the purpose here is to produce additional thrust instead of to increasing the turbine work output. So that's a similar to the reburning or reheating. In Brayton cycle, but these two are for the different purpose that you want to be clear. All right, that's basically everything for the first chapter, which is for the gas turbine cycle. So we are going to move to the next two chapters, and they are dealing with different type of process. Not only in terms of the there are different type of cycles, and they are also different in terms of the working fluid that being used, and that is related to how do we do the calculations in calculating those two cycles. So let's have a quick overview of the different type of cycles. Right. So the gas turbine cycle is one type of gas cycle, or I should say it's gas power cycle, and that including the gas turbines, which we discussed here, and also including two other cycles which we do not discuss here, but you should have some idea which is called a diesel and Otto cycle. So we are not talking about here. If you're taking advanced thermal, we will have some discussion there. But the common of this three type of cycle is called gas power cycle. So there the working fluid is gas. By gas we mean ideal gas. Right, and the purpose of this cycle is just to produce power. So the working fluid here is ideal gas. In terms of calculation, if we know the subject is ideal gas, then there is a set of equations that we can apply related to ideal gas law, isentropic relation. Those all can be directly applied. So PV equals to MRT can be used. Ideal gas isentropic law can be applied safely to ideal gases. And in addition, during our discussion, there is some fundamental first principle laws we use extensively and repeatedly, which is first law. So for every step in the cycle, when we analyze the very first thing we do is to apply the first law, right? So that's the starting point for all the thermodynamic analysis. So these are the equations that you can use, and when you're dealing with gas cycles, the calculation can be based on the ideal gases. All right, so that's different from the cycle we are going to discuss from today. That's called a vapor cycle. So we are discuss two types of vapor cycle. One is refrigeration, and the other is steam power. So these are two types of vapor cycle, and the working fluid here is different. The working fluid here actually is a two-phase. It's always exists in two-phase, or always involving two-phase in the cycle. Certainly, the two phase is a vapor and a liquid, right? And for the vapor and the liquid, or vapor and liquid, they can coexist in the process, or they can exist as a single phase there. But it's always involving a process called phase change, which we are going to have some discussion in a minute. So it's always involving phase change, going from liquid to vapor, or vapor condensed to liquid. And here the important to notice that when we're dealing with vapor as in single phase, so for certain process they're only involving vapor in the process, but you do not want to apply the ideal gas law to the vapor. All right? Even though it doesn't involving two-phase flow, only involving the vapor, but the ideal gas law does not apply. So that's something you want to be aware of. And the reason is the assumption, or in order for the ideal gas law to be valid, the condition is there is a minimum interaction between the gas molecules. But that's not the case when the gas or when the liquid being just turned into vapor. There is a significant interaction between the gas molecules. So you do not want to ideal gas law. Instead, in the calculation, you want to using something called the property table. All right, which means if you dealing with vapor, do not apply ideal gas law. You need to go to the table. Here we're using table, or some other cases you can use using just the chart. So you go to this reference data and to find the entropy, specific volume for the given condition, right? So you need to use a table extensively in order for the calculation. And certainly there are different tables being used for different phase in terms of saturated mixture, vapor, and even pure liquid. Right. So this is something we want to be aware of. And certainly, during the calculation, as similar to the gas cycles, we still based on the first law. First law always valid regardless the working fluid, and also we are using the same principle as we also used in the gas cycle. Maybe I should add it here, which is the state postulate. State postulate we don't use, we don't recall it very much during our calculation because ideal gas law relation often is enough. When we're dealing with vapor cycles, it's important to be aware that if you know two states or to say for a given state, if you know two independent intensive properties, that state is defined for the system. Which means if you already the system is defined and you want to find any other properties, for example, enthalpy, entropy, any other properties, you can just go to the table and use it. So that's something you need to be aware. As long as the state is fixed, which means you know two independent intensive properties, then just go to the table to find the rest from the table. All right? So it's always there, and be aware of that when you're using it. All right, so that's the major difference between the two types of cycles. So let's say a few words about the phase change. Phase change is a common phenomenon happening in nature. So here we're only dealing with the liquid to vapor process, or vice versa. So if we consider a phase change process, if we draw a phase change diagram in terms of temperature, and here I want to use volume because that's more convenient and more straightforward. Later on, we will convert this to the TS diagram, which is in a similar shape. So for the phase change, if we have water, all right? So if we have the water at the room temperature and we want to turn it into boiling water. So let's say if we have something here at 20 degrees C, say that's 1 atm. If we're starting from there at a certain initial volume, if we heat the water, what happened to the volume? Volume will increase. Temperature? Yeah, I hear someone said the volume will be the same. Yeah, that's mostly correct. The volume will still expand to some extent, but certainly much smaller compared to gas phase. So it will not be staying the same. It will still expand to some extent. So if I draw this, the temperature will goes up, but the volume actually will goes up as well. But it's a very steep slope because the volume change is very small. So that's actually a pretty good point. Then if I reach the 100 degrees C, the water will start to boiling, right? And during that process, how should I draw this process during the evaporation or boiling process? Horizontal line, which means the temperature does not change as long as the pressure does not change. So it will be a horizontal line, or make sure this is horizontal. All right. So then the end of it will be all the water turn into vapor. Right. So that's the end of it, and after that it will be steam. Right. So how should I draw the next step in terms of the temperature versus volume? Will be more or less like a gas. So we'll be similar like this, but with a gentle slope, because in that case the volume will goes at a much larger, much higher rate compared to the liquid phase. So we define this state as a compressed liquid, and this state as the overheated vapor, and the state or the process during the phase change is called a saturated mixture. And in particular, at this point, it's called the saturated liquid, where the liquid is just about to boil, reach the boiling point, but have not boiled yet. And this case is this point is a saturated vapor. So all the liquid is vaporized, but still at the boiling point, right? So that's some there's some term defined on the phase change process, and so this is basic stuff. If I change the pressure, for example, if I go to highland, for example, if I go to Tibet, right? Tibet has an average height about 4,500 meters. What happens there? The ambient pressure will be lower. What happens to the boiling point? Will also be lower. So that's correct. So if the temperature, if the pressure drops, the temperature for the boiling point will also drops. So that's saying that this is only for one atmospheric condition. If I change the temperature or change the pressure, I will have a different line, but still have the similar process, similar shape, right? So if I have T, V, so if that's 100 and that's 1, if I want to be more exact, that's 1 bar. 1 bar corresponding to 10 to the 5th Pascal, which is very close to the 1 atmospheric. And if I go to highland, then I will have lower pressure. For example, if this pressure becomes half bar, this boiling point will drop to 80 degrees C. So in fact, if we consider the ambient pressure in Tibet, average height will be 0.57 bar, the water will boil at around 85 degrees C there, right? So if for certain cases, because we're boiling water, in many cases we want to kill the bacteria or germs in the water, right? But in that cases, if the water is not reaching 100 degrees C and they start boiling, then you consider it's okay to drink and you can get sick. So that's lower pressure. If we go higher pressure, this line will move up, and then there will be, for example, if I go 2 bar, the boiling point will go to about 120 degrees C. So when you go high pressure, this phase change or this horizontal section will become shorter and shorter. So if you keep going until a threshold where you will have basically the length of the horizontal section will shrink to 0. So this one is called critical point. Or critical condition. So for water, again, I should say this for water, right? For water, this critical condition corresponding to 220 bar and a temperature about 374 degrees C. So that's a critical point. So above the critical point, that's called the supercritical fluid. So in that region, there is no difference in terms of vapor or liquid. So it's just they call the supercritical state. All right. So when we have this set of lines, right, we can connect them together in terms of the starting point and the end point on the horizontal section. So if starting from the critical point, then connect all these saturated liquid point and all the saturated vapor point, then I have this red dome-like curve. So on the left, as we called saturated liquid line, and the other is saturated vapor line. And the whole thing is called the saturation dome. So this is our, basically, when we have the, when we discuss the vapor cycles, this is our reference line. So when we later on draw the TS diagram, the very first thing we draw on the TS diagram is this saturation dome. This is our reference line, and the different states, different processes is working around this saturation dome. Right? So that's the a few things related to the phase change process. Why are we dealing with this phase change, or why are we dealing with vapor cycles? Why we just having all the power cycle running on the gas cycle, which means the working fluid is always ideal gas, right? Why dealing with the two phase cycles? So the reason for that is during the horizontal section, or in the process when the cycle going through the horizontal section, there is a large amount of heat that is being released or absorbed in the process. So for example, if you taking the water, again, the heat of vaporization for water, again for water at 100 degrees C, that's about 22,050 kilojoules per kilogram. So 1 kilogram water can, when it's vaporized, it will absorb this much heat, and when it's condensed, it will release this much heat. This is a huge amount of heat compared to you heating and cooling the air. So if you consider the what's the CP of water, all right, liquid water is about 4.2 kilojoule per kilogram. So this much heat corresponding to the heat that you heat the water about 500 degrees Celsius. Raise the temperature by 500 degrees Celsius. That's a very, very large amount of heat in the process. So if you have the CP of air, which about 1 kilogram per kilojoule per kilogram, which means you can, if you can do that, you can raise the temperature by nearly over 2,000 Kelvin. All right. So when you're running on the vapor cycle, you do not need to dealing with that large temperature change. The thing is happening in a constant temperature. So in terms of when you have the high temperature device, the whole system become expensive. Everything has to handle, if it can, it will be expensive. And for some cases, if for 2,000 Kelvin, there is not much material and not much device that can handle that high temperature. All right. So this allowing you to dealing with a large amount of heat or enthalpy transfer in and out of the system without having a very high temperature process. All right. Another thing we want to be aware of, we said the boiling temperature will be changing with respect to pressure. So in other words, the temperature and the pressure, they are not independent intensive properties during the phase change process. So during this horizontal process, the temperature and pressure, they are independent. They are dependent on each other, right? So which means we lost one of the important independent intensive properties. So we need to define another one to describe the process. All right? So that's what we are going to discuss in a minute. So temperature and the pressure depends on each other during phase change. So you know the temperature, you know the pressure during the phase change process, right? Not necessarily for this compressed liquid or superheated vapor line, but during this horizontal line, that must be the case. So we define another independent extensive properties called quality, which is more refers to the vapor quality, and this parameter actually initially being defined for the steam. So we use it in general for the vapor quality, and the other one is defined as, we use X for it, defined as the fraction of the vapor in the total mixture. So in this horizontal line, you would have the, except at the start and the end point, you would have the gas and or vapor and the liquid coexist. So the quantity is defined as the fraction of the vapor in the total mixture. All right. So this one is a intensive and independent I should say can be used as intensive independent property to define states. So in other words, if the problem tells you or you calculate the X, that's one of the intensive independent property already known for the state. And if you know the other one, the other intensive property independent of the X, then the state of the system is fixed. All right? So this is actually is often used property for defining state when we dealing with the vapor cycles. So from there you can calculate the enthalpy of the mixture. Can be calculated X times the enthalpy of the vapor section plus the 1 minus X enthalpy of the fluid or the liquid section. So maybe I should say this for vapor and this is for liquid. All right. So vice versa, if you know the enthalpy of the mixture, you can also figure out what is the quality, which means what's the fraction of the gas vapor in the mixture. So that one can be written as H G minus HF and H minus HF. So if you figure out or you calculated the enthalpy of the mixture, then based on this, you can find the quantity and then define the state there. All right, so that's the one. And also I should just, in other cases, you can figure out the entropy of the process. So that's the similar one. If you're going through a isentropic process, the start and end will have the same entropy, and if that end state is in the saturation region, then you can using that to calculate the quantity of the mixture. All right, so that's just a few things before we start the discussion of the first vapor cycle. All right, so that's the start of the chapter 3, which is for the refrigeration cycle. Refrigeration cycle is something we can consider is working against the nature. The nature wants to transfer heat from high temperature to low temperature, but the refrigeration cycle working against it to want to make the cooler space even cooler and the hot space even hotter. So if you looking at the principle there, it's based on something called the reverse Carnot cycle. Reverse Carnot cycle, which means if you have a hot reservoir and you have a process working between the hot and the cold reservoir, right? So when you have a Carnot engine, you're taking heat from the hot reservoir and doing some work as output and dump the unused heat to the cold reservoir, right? So reverse the cycle running in a reverse manner. So you have the cycle starting to pick up heat from the cold reservoir, which we said low temperature heat, and then you want to dump it to the hot reservoir, high temperature heat. But you cannot do that just in this way, right? You cannot dump a certain heat at the 25 degrees C to the 100 degrees C. That's impossible based on the second law. You cannot remove 100% of the heat from a low temperature reservoir to the high temperature reservoir. You have to do something to make this happen, which means you have to have some work input in order to drive this process to happen. So there you have the QH equals to the Q low plus the input work. So in terms of the application of this type of cycle, certainly we know it's the refrigerator working principle there, and another common user device also running on this type of cycle is yes, heat pump is indeed one of this, and what else? Which is even more common than the heat pump. Yes, AC, air conditioner running on this type of cycle. Air conditioner is to cool the room and in summer, right? So if you consider this device, so I should say application, all right? Application including the refrigerator, including the air conditioner and the heat pump. So air conditioner and the heat pump how many of you know what the heat pump does? It's a heater. It's a heater. How? What's the working like? What's the process or what this heat pump does? It heats the room inside, right? And that's not happening in summer. It happens in winter, right? Typically happening in winter. And when outside is cold and you want to move some of the outside enthalpy outside, move some outside heat to the inside. Inside actually is already warm than the outside, right? So if you understand the process, the heat pump and air conditioner is working on the same principle. So you need the air conditioner in summer because you want the inside to be cooler than the outside. But in the winter, you want the opposite. You want the inside to be even warmer than the outside, right? So if you consider this cycle is running as AC, which means you have this is your inside, or I should say the room inside. All right. So that's the space that you want to cool. And a heat pump is working on the same process, but it's just switch the inside and outside. So if I have a heat pump, maybe I'm using the red one. So you can run the same device as a heat pump. But in that case, you want the cold place stay cold and hot place being even warmer, right? So there, that's your inside. So it's the same device which can make the cold space even colder and a warm place even warmer. Certainly, you when you have a unit, you cannot switch inside and outside. Right, you cannot switch your room to the outside based on what we're showing here. So a modern air conditioner has been designed in a way it has a switch built-in. So in summer it can working as an air conditioner to make the inside cooler, and in winter you turn the switch, then it will not switch, certainly not switch the space, but it's just switch the process so that you can move some of the outside thermal energy or outside heat to the inside to make the inside warmer. Right? So it's the same device, but just running on the opposite way to serve two purposes. All right, so let's continue on Friday.
Take a photo of some I missed.
For the optimus process, first for the brain only work for a turbofan because it needs the oxygen. Because after turbojet, you go through the combustion, and then if you additional fuel, so there still be enough oxygen before the nozzle.
Yeah. So for the gas turbine, gas turbine always running at the overall lean condition. Lean, which means you have the fuel is less. Yeah. So it's never run stoichiometric. It will be too much like suitable, too much suitable. Yeah.
Well, about the assessment,
The assignment will be, it will be handed out later this week. It will be out. Yeah, I'll send you email.
Sir, I want to take photo.
Some information I got.
Okay.
Yes.
네, 이거는